All right, for some reason the video cut off before, so I will just start the second part up. I was mentioning that about my class averages, that my class averages don't vary very much. I would say in statistics, normally class average is like an 83. Um, just off the top of my head, I've probably had class average as high as like 85 or 86. Maybe one as low as like 78. So they don't vary nearly as much as the student individual ones, because as a group, it's hard for the group to vary as much because there's more people and you're averaging them all together. So basically, as we get more people, the standard deviation goes down because it's harder to vary with more people. So this formula, this is the way we get the standard deviation for that normal curve that we saw. Basically, sigma, that's the Greek letter sigma, stands for the population standard deviation. So if we know the population standard deviation, we divide, that's for an individual, we divide it by square root of n, where n is the sample size. So the box, if you were to, how would we find the standard deviation of that normal curve you saw? We would have to know the standard deviation of the box and then divide by, if you would have taken samples of 10, square root of 10 would have gotten you the how the normal curve would have turned out for the sample distributions of size 10. So once again, I could use this on the student example. If students normally have a standard deviation maybe of 25 points, if I end up having a class of 30, I'd have to take the 25 and divide by the square root of 30. That would shrink the individual standard deviation down and would make the class a lot harder to move around. So the standard deviation for a group will be less than the standard deviation for an individual. The way you find that is you take the individual standard deviation and divide by square root of the group. It comes from the variance rule. You don't need to know that, but that's basically the formula is derived from using the variance over and over and over again. All right, so that's where that square root comes in. So let me show you how to use it. So the first thing when using these is being able to separate proportions from means, because we just did a whole big thing on proportions, and now we're going to start doing a thing on means. So when you go to do your AP exam, you're going to have to know which one to use. Basically realize that all the stuff we were doing before this was proportions. Proportions are percents. So if you have any kind of thing that can be represented as a percent, and they're usually used for categorical data. So like yes and no, success, fail, for and against. So like when we're talking about, do you like Donald Trump or do you like Obama? That was sort of a for or against kind of question. It's something that fits into categorical data and fits into being a percentage. What we're going to work on now are means, and means are averages. We use them with quantitative data. So times can be averaged, weights, heights, like the years in the box, things like that. So going forward, we don't want to forget about the proportion stuff that we learned. At the end, we're going to talk about how do we know which procedure to use. But for now, we're not doing any of this stuff anymore. We're going to look at things that have averages, okay? So the box had an average, year in it. And there are other things we can find the averages of. So let's look at using means. So here's an example. There's a college math entry exam, we'll just say for a college, and we know the stats on it. Basically, on average, kids finish this in 34 minutes. So this is an individual finish in 34 minutes. The standard deviation for individuals is 5 minutes. So now 70 students are going to take the exam. Now, I want to contrast here the difference between solving it for an individual, which we would have done before, and now using a sampling distribution for the sample average of 70 to figure out how likely the second part is to happen. So part A is for one student. What is the probability that any given student will take more than 40 minutes? Part B asks, what's the probability the entire group that you're having 70 students take the exam? What's the probability 70 students will take more than 40 minutes? Remember that an individual is able to vary a lot more than the group. So I'm going to show A and B on the board behind here. So the left side shows A, what happens with one student. Let's see if we can get that glare out of there. There we go. So what happens with one student. They told me that for one student, the average was 34, and for one student, the standard deviation, that's why I'm using the sigma, so for all the students, the standard deviation is 5. This we would have done earlier in the course, because basically we figure out what's the probability somebody takes more than 40 minutes, given that everything's normally distributed. Well, we would find a z-score, so, and we'll assume that it's a test, that the times on the test are normally distributed. I don't think I put that in the problem, but let's just assume that. So we'd find a z-score. We'd go, well, 40 minus 34 over 5, so the real value minus the mean over standard deviation would tell us how far we were from the center, 1.2 standard deviations. We can now use the calculator to figure out how likely it is to be 1.2 standard deviations or more. So what's the chance somebody takes this long or longer? How unusual is that result? Well, it comes out 0.11506. So basically a single student will take more than 40 minutes 11.5% of the time. Or if you had a big group of students, you'd expect 11.5% of them, or I guess I should say if you have one student, the chance this one student will stay there and take that long is 11.5%. Now, what's the chance the entire group of 70 students would take that long, would take an average of 40 minutes? So now this is where the notation gets a little tricky. Remember the mu for the x-bar saying the average of the sample averages. So the average of the sample averages should be the population average. So this number doesn't change. If you had 70 students, the most likely event would be that they would take 34 minutes, just like an initial student would take. The issue comes down to the standard deviation. What is the standard deviation for the averages? Well, the standard deviation for one person was 5. That formula I showed you, the standard deviation for 70 people is 5 over the square root of n, or the square root of 70. The spread for 70 people is a lot tighter than the spread for one person. So the group of 70 only varies 0.5976 of a minute within one standard deviation. So now notice how this has an effect. What's the chance all 70 students would have an average of 40 minutes? Well, we would take 40 minus 34, but now divide it by the group of 70's standard deviation. And that's 10.04 standard deviations away. That's a lot farther than the individual. So when I put this in normal CDF, I got one of those e to the negative 24 or whatever. I just thought it was funny to put all the zeros down. So it's 23 zeros and a 5. Basically, it ain't going to happen. So the chance that the entire group takes an average of 40 minutes is virtually impossible. But notice the contrast between finding one student's information and a group of 70 students. It's not uncommon for one student to take more than 40 minutes, but it's extremely uncommon for the average of all 70 students to be over 40. All right. This uses just a regular normal curve. This uses the sample distribution. So this is what samples of 70 would look like. And basically in a distribution, if you were doing samples of 70, taking their averages, you'd basically never get their average to be 40. Now, I had mentioned them being normal curves. This doesn't have to be a normal curve, but even if this were some other distribution, this would still come out normal, all right? So regardless of what this thing looks like for one student, this distribution for 70 would look very, very close to normal if you actually did the experiment over and over and over again. So I did make the one student normal just to make it easier, but this, even if this weren't normal, we wouldn't be able to make this calculation, but we'd still be able to make this calculation based on the fact that 70 students, the sampling distribution will come out normal, even if one student isn't. All right, let's look at one more example, but first I'll let you try one. Oh, let's see if I can get this to... All right, doesn't want to go. There we go. All right. So, oops. Here's the one I wanted. We'll do that other one next. So, try this one on your own. I'm going to just put it up, and then you can try it, and I'll put in a second video the solution. Basically, it's about... I can't use Frosted Lucky Charms because... and they're, you know, magically delicious. That's trademarked. So I decided to go with Frosted Schmucky Farms, and they're tragically suspicious. So we'll use those because that's not trademarked. Basically, pretend that the boxes have an average weight of 16.4 ounces with standard deviation of 0.2 ounces. The boxes are actually labeled 16 ounces. So this is not uncommon in real life because basically they don't want to go under the advertised weight, so they usually put a little more in. That way they're close to guaranteed that they'll meet the weight on the box and they don't get sued. So see if you could figure out, basically like the other problem, what's the chance a single box will be under the labeled weight? Assume that all these things are normally distributed, that the individual is as well. So what's the chance a single box will be under the labeled weight? And then if you had an average weight taken for a case of 40 boxes, so you're going to look at 40 boxes and take its average weight, what's the chance that this average is under the advertised weight? So basically, what is it for one box? What's the chance 40 boxes are under that advertised weight? All right. So it's similar to the other problem I did. Give that a try. I'll give the solution in another